Hi, everybody. My name is Nathaniel. I'm a PhD student at Purdue. And I'm here to talk to you all today about some work I did with my advisor, Dr. Abulhair Saparov, on evaluating theory of mind in language models. So, for those who don't know, theory of mind is the ability to understand and reason about the perspective or mental state of another person. This is something that was actually measured in humans, especially children, because people were interested in when this uh, ability develops, using this test called the Salian test, which I have an example of up here. But essentially, it's you provide a person with a story. At a high level, it's just a story with two characters within some environment. One character modifies the environment somehow. So, like in this example, Sally puts a ball in a basket and leaves and moves the ball to another box. And then you ask, where will Sally look for her ball when she comes back, right? And you need to reason that Sally has a different perspective than Anne, so she's gonna look where she left it, and that would be the basket. Um, so this test and many tests like it were developed to test theory of mind in humans. And so naturally, people wanted to evaluate this ability in LLMs the same way that we do to humans by providing this test to LLMs in a study in 2023. And it was initially found actually that LLMs do pretty well on the Salian test, but a different study found that if you made really trivial alterations to the Salian test, like for example, making the box in the basket clear so it's obvious where the ball is, LLMs will fail and instead respond as if they're answering the original Salian test. So it's clear that there's some kind of memorization or pre-training data contamination going on here. And to that end, we looked for a way to understand LLM theory of mind abilities in a way that's more robust to data contamination and at the same time minimizes confounding factors, right? We want to evaluate theory of mind and theory of mind only as best we can. And so that's what led us to the creation of StorySim. So it's a framework we created essentially that takes in a set of high-level events, which we call a storyboard, um, and generates these stories such that they satisfy all the events provided by the storyboard, and at the same time induce as much randomness as possible to create more diverse stories. But in our experiments, these stories look like characters just moving around different rooms. It's a really simple setup. And what this allows us to do is then use these stories to ask theory of mind type questions to LLMs. So using these stories, we come up with two kinds of questions that we'll go over. So there's what we call the first order theory of mind task, which is this exact example we have here, right? You have characters moving around in a room, and then you ask, where does Bob think Anne is, right? So the LLM has to reason about Bob's perspective of Anne. And then there's a second order task, which uses the same exact types of stories, but steps up the amount of reasoning you have to do through mental states. And you would ask something like, where does Bob think Anne thinks Joe is? Um, and so these are the types of stories we created using StorySim. Um, we set the storyboard up so that it essentially just has a bunch of characters meeting in one room. We call that the first common location. And then from there, characters will move around such that each of them will have a different perspective on where the other one is. We kind of fix the rule that if you're in a room with a character and a character leaves, you know where that character went. But then if they move further, you no longer have an idea of where they are. And I'll just point out this amount of time it takes for you to no longer know where they are. We call that the mislead distance. That will be important later. But to this end, like I said, we generate 100 stories using similar storyboards um, for the purpose of evaluating theory of mind in LLMs with first and second order theory of mind tasks. And we ask two questions. So first, can we evaluate theory of mind in LLMs in a way that's robust to the use of heuristics, as I talked about before, or any kind of like data pre-training memorization? And then secondly, using StorySim, we wanted to see if we could compare the theory of mind ability of LLMs to just a general world modeling ability, right? So reasoning about the perspective of one character in a story and the perspective of another character is kind of seated in your ability to model the entire world that the entire story that the entire world that the story takes place in, right? So we want to compare the ability of theory of LMs to reason through theory of mind in comparison to their general world modeling ability. So for this first question, as I said, we generate 100 stories varying what I call the mislead distance across a few different values and compare LLM performance across that for both first and second order tasks. Notably, some models do pretty well in the first order task. O3 mini pretty much aces it, but at the same time, you have models like GPT-4, which actually have a pretty varied performance across different mislead distances. You even see DeepSeek R1 do better as mislead distance increases, maybe indicating that it's better at tracking mental state changes and state changes that occur closer to the end of the story. And then in the second order task, you see a lot of models not do as well, right? O3 mini, which pretty much aced the first order task, becomes the worst LLM in the second order. So it's pretty clear that LLMs struggle heavily with the second order task. Even with the first order task, there's kind of a wide range of performances. And it's interesting because newer slash more parameter type models don't necessarily always do better, right? So O3 mini gets outperformed by GPT-4 in the second order task. Llama 4 Maverick, which has more parameters than Scout, gets outperformed by Scout. So some interesting things there. Then looking at these experiments, because StorySim is, again, so easy to parse, we compared the outputs of these LLMs for a few of them, GPT-4, DeepSeek, and O3 Mini, to essentially the like reasoning, the character movements throughout the story. And then we asked, what are the locations that the LLMs are memorizing when they're not answering these theory of mind questions correctly. Interestingly, it's actually kind of hard to get these LLMs to respond at all, right? So we saw a lot of cases where GPT-4 and DeepSeek R1 just refused the prompt entirely. So that'd be GPT-4 saying not enough information. That would be DeepSeek R1 reasoning itself to death, right? It's running out of context length. So there's a lot of that, but when models do respond, most often they just repeat the first common location that all the characters intersect at. So there seems to be some kind of memorization of that specific point in the story. But then tracking the mental states of all the characters past that is something that LLMs tend to struggle with, potentially indicating that there's kind of a lack of an internal representation of all these states as the story progresses. This is especially true with O3 Mini, and it actually completely almost explains why it does so poorly on the second order task. And so now moving to our second question, comparing theory of mind to general world modeling ability. We came up with an experiment where we first just repeat the first order theory of mind task given a story. And then we create a second prompt given that same story where we kind of reduce the theory of mind task to more of like a world modeling task by just taking the algorithm that you would use to answer the question and prompting the model with it, right? So in order to know where A thinks B is, you would go and find where A and B intersect, and then where did A watch B go? So we prompt LLMs with that as well. And then we take that a step further by then replacing all of the human names and occurrences of humans with inanimate objects and comparing the world modeling ability when humans are present to when it's something inanimate instead, pencil or shoe or something like that. Interestingly, we find that theory of mind is actually like a pretty good rough upper bound of world modeling ability. There's no models that, I mean, there are actually a few exceptions, but most models that do poorly in theory of mind also do poorly in world modeling. It seems that world modeling ability over humans is actually a pretty good indicator of theory of mind performance. And interestingly, when given the same exact question and story, but comparing humans versus inanimate objects, LLMs do better with humans, indicating maybe that there's some kind of better state tracking that happens when you mention human names. Looking at the Llama 3.1 family of models, restricting that architecture and just looking at the number of parameters, we noticed that theory of mind performance was increasing as you add more parameters. So we wanted to concentrate on the same model family, looking at parameter size in a 3-shot setting And again, we noticed that theory of mind seems to correlate pretty well with the number of parameters. So those are kind of the high level takeaways from our story. Seems like maybe LLMs don't have as sound of a theory of mind as initial tests indicate. It's pretty easy to perturb these stories and get them to mess up on our questions. And again, our questions are it's a very simple benchmark. Really, the only source of complexity comes from tracking the mental states of these characters. And we also find that general world modeling ability may be a good indicator theory of mind. That's it for our talk. We think this is kind of an important thing to study as LLMs become more responsible for critical decisions. And yeah, I think I'm out of time. So. Yeah.